Good morning. We will continue with unit 2, and we are back to the whiteboard, sorry, our traditional blackboard. We made some changes to the camera settings also. Imparters came to the classroom and they have tried to make it a little better. And we have also opened the curtains. Apparently, that was one of the problems. So we will try this for the next few classes, mainly because unit 1 is almost over. There is still one or two topics. We will come back to that later. But other than that, as you saw, unit 1 was mostly a lot of introduction, definition to a lot of new topics. So it was easy to work with PowerPoint. But once we have more detailed um, topics like what we have in unit 2, unit 3, etc., it will be little difficult to continue with the PowerPoint, especially when we have a lot of diagrams that we want to show you, a lot of equations, numericals, etc. So this unit definitely, ideally, this is the best way to do it. And of course, the video will be shared with you, so you can go through it any number of times. But like I said, always better to maintain a notebook like we are writing here. You can write down whatever you feel is important, whatever we are writing in the board. Okay. So Unit 1, we have covered around 80 to 90%. There is just one more topic with regard to scaling, which we have to discuss. And because some of this information is required for that topic, we will come back to that at the end of this unit. Maybe we will spend one class with respect to scaling alone. And then it will be easier to understand that topic. So that this thing we will do it after at the end of this unit 2. Okay. So unit 2 is very different from unit 1. Unit 1 was at a very high level about a lot of things about the overall VLSI process. The main objective of unit 1 was to introduce you to the VLSI industry, the industry perspective, the practical perspective, because a lot of subjects that you're going to start studying in 5th semester, of course, they are quite theoretical, and there will be a lot of theoretical aspects also. But you have to remember that many of these subjects are also job descriptions, especially in VLSI, embedded, etc. These are all very, very other than IT, of course, is the single biggest employer in India. But in the high-tech domain, VLSI is also a very popular employer, especially in Bangalore and Hyderabad, etc. So a lot of these definitions are very important for you to understand what is the meaning of this industry, what types of jobs are there in India, which we have discussed during the course of the first unit, and what exactly is the overall flow, where will I fit in as an engineer, etc., etc. So that is, of course, important, but also it is important for you to understand, right, what is happening at the transistor level. So we will do a complete switch. We were talking about huge systems, VLSI design flow, etc. We'll go completely in the opposite direction and come back to that one single element, which is the transistor. So unit 2, okay, the first Mos transistor. This is a single most important topic of this unit. What is the structure? How does it operate? What are the equations for the current flow through the transistor, etc. Then once we look at the transistor, okay, so inverter is a very important circuit in CMOS VLSI design. because there are hundreds of gates, right? I mean, there is inverter, which is the simplest gate. We cannot make any gate with one transistor, so inverter has two transistors, one NMOS and one PMOS. We will see the circuit, of course, but a lot of the other properties of the circuit, there are many other properties, as we will see, we can describe in detail for a inverter. Okay, in particular, we will look at the transfer characteristics. What is the meaning of this transfer characteristics? In transfer characteristics, we are interested in the relation between input and output. So for any circuit, you have to give an input, right? It might be voltage, it might be current. In digital VLSI design, especially, it will always be voltage only. We don't care about the current as such. The voltage will be the input. Okay, it will be a signal, for example, A, B, C, and the output will be the output of the gate. What is the relation between the input and the output? So we will do that analysis for the inverter, and for the rest of the circuits, okay, we won't do this analysis because there are so many gates. Like we discussed, we have a library might have 1,000 gates, right? We can't keep doing this analysis for every new gate that we come across. Luckily, we have a good characteristic, that is, any circuit, okay, we can convert to a equivalent inverter. That is, I have some circuit, it might have some 20 or 30 transistors. I can convert all of that into equivalent inverter. Then whatever analysis I have done for inverter, okay, I will just do it for that equivalent inverter. I will get the properties of my full gate. That is the trick that we generally apply. So we will not do this analysis for every gate. Okay, we will just look at the inverter, how to determine the transfer characteristics of the inverter. So that inverter is the simplest circuit. From that, we will go to CMOS circuits. Now this top is the transistor. Okay, there is no transistor called CMOS transistor. CMOS is the name of the fabrication technology. Okay, what we studied in the previous unit, photolithography, NWEL, NWEL, PWEL. If you remember, NWEL, PWEL allows us to make both NMOS and PMOS on the same substrate, whether it is P-type substrate or N-type substrate. So this fabrication technology, where we are able to make this N-well and P-well, allows us to put both NMOS and PMOS on the same substrate. That fabrication technology is called as CMOS. Okay, and whatever circuits, CMOS circuits. So CMOS circuits will have both NMOS and PMOS transistor. The transistor is called a MOS transistor in general. Okay, so the next part of this unit, we will look at CMOS circuits, so NAND gate, NOR gate, any gate, right? Any particular logic function. If you want to convert it into a circuit or a gate using our MOS transistor, how do we do that? And along with that, we will also look at layout or stick diagram. Both are equivalent, very similar to each other, but layout we have seen. Layout is the final output of the fabrication process. For simple circuits that we will see, we will also see how to draw the layout by hand using a scale and pencil. And similar to layout is stick diagram. In layout, every wire, every transistor, this thing has to be in terms of sizes. Okay, in stick diagram, it is a simpler representation. We will just represent it by a straight line. That is all. They're both equivalent to each other. And the last topic in this unit, we will also see just one. We are interested only in one type of sequential circuits. This is not like, for example, in third or fourth semester, you might have done digital electronics. We have so many types of flip-flops. We have Moore machine, Mealy machine. We are not interested in all that. Okay, we are interested only in one type of sequential circuits, that is D. Okay, if you remember D flip-flop, here also we are only interested in D latch and D flip flop. We are not going to look at J, K, T, R, S. All that is not going to come into the picture. But only thing, instead of treating it as a gate, we will look at the circuit. Okay, so circuit is a very important terminology in CMOS or in general VLSI. Okay, there is gate level. In gate level, we use gate level schematics. For example, this is a AND gate, right? Like this, there are so many gates, NAND, NOR, XOR. You have a symbol for every gate. But when you are talking about circuit, this is not the circuit. Okay, this is a gate level diagram or a logic diagram if you want. When we are talking about circuits in particular, it means that it should be in terms of the transistor. So remember this distinction. Okay, it's very important. It's this thing, basic definition. Circuit can never be in terms of these symbols. Circuit should be in terms of the transistor level. Layout, of course, is in terms of the rectangles, etc. So every representation is fixed. Okay, so we have to remember these. Depending on the question, you have to answer accordingly. So this is the overall topics in unit 1. So we will start with the most important topic, of course, is the MOS transistor. Okay, sorry, unit 2, not unit 1. So we'll just redraw. Okay, so our transistors, they are very similar to each other, NMOS and PMOS, and also they have the same structure. Okay, that is, if you take the mirror image, they are both the same, left hand side and right hand side. So this is one difference from BJT. In BJT, emitter, base, collector, E and C is different, emitter and collector. Here also they have two names. Okay, that is, this might be called source, and this is the drain. This is the source. Okay, so we'll call this S, we'll call this D. They have different names, but in terms of the structure, they are identical. Emitter and collector are slightly different in terms of the doping, but other than that, they are the same. Here also, they are the same. Okay, that is the first thing. And the second thing, in this very small shaded region here and here, okay, so this is the gate, tin, both NMOS and PMOS. Okay, this is the gate terminal. So if you want, I can write that this is G, this is also G, and this is the gate Okay, so in both NMOS and PMOS, it's identical gate terminal, and this is the gate terminal, and we can apply voltages at these three. Okay, we will never measure the voltage. We really don't want to measure the voltage. So basically, we have control over all three terminals, that is source, gate, drain. We don't care about measuring any of these voltages. We will give the voltage. We will only see the effect of the transistor as a switch. Okay, so for example, here we have switch on or off, right? It can be only in two positions, and it will have left hand side and right hand side. The left hand side, right hand side, same, source and drain. So the gate doesn't actually take part in the switch connection, but of course it is very important because the on off is controlled by the gate. Okay, so in all of these three terminals we can apply the voltage, that is they are under our control. Through the electrical connections we can apply a voltage in all of these three terminals. We never want to measure. In VLSI generally we don't measure anything anywhere in digital VLSI. We will just either it will be 0 or 1, and that will be passed on to the next stage. That is all that is being done through the full logic circuit. Either it is 0 or 1, it is given to the next stage as an input. Based on that input it will produce the output, and so on till the primary output, which will come out through the circuit through the pin. Okay, we saw the pins in the fabrication. Those are only primary outputs, and there also we will not measure anything. It will just be at 0 or 1, because digital circuits means input is digital, output is also digital. So it will be 0 or it will be 1. That is 0 to VDD. Only two values of voltage for digital VLSI circuits: 0, which is considered ground, power supply, or VDD. Okay, it might be 1 volt, 1.2, 1.5. That depends on the design. So this is the structure, and if you remember, in a NMOS transistor, okay, source and drain are of type N plus, and this should sit on a P type substrate, or it might be a P well, that depends on the fabrication. For now we will just assume that it's sitting on a P type substrate, no problem. Okay, and necessarily there is a fourth terminal, but generally we will not control this terminal. That is, this is the source, drain, gate, and the fourth terminal is called as the bulk or substrate. Okay, it might be confusing to call it substrate, because already this is called S. So because of that it will be called as the bulk terminal, or with the letter B. Okay, so that is the fourth terminal called as a bulk terminal. So these are the four terminals. The fourth terminal, okay, in this I have shown it is connected to ground, and you can try to remember. Okay, we have discussed this before, why it is connected to ground. We have discussed this before, but it should be connected to ground, otherwise it will not work at all. Okay, similarly on that side, the bulk terminal, okay, since it is a PMOS transistor has to have a N-type substrate or a N-well, okay, doesn't matter. But that N-well or N-type substrate should necessarily be connected to power supply or VDD. So upward arrow generally means VDD. Down arrow, this we have seen, this generally means ground. Okay. So the fourth terminal connection is there. Okay. It's not left floating, but we don't control it. Generally the fabrication, whenever they're doing it, if they know it is a digital circuit, automatically this connection they will do off. We don't have to do this connection. So the three terminals are the ones which are under our control. We can give a voltage and we can get the output. So this is the structure of our MOS transistor. This is NMOS, of course. This is PMOS, and of course circuit symbol. We said that we are drawing circuit diagrams, right? What diagram is this? This is the cross section, okay, of the transistor. This is called as a cross sectional diagram, or every time I want to draw a circuit, okay, this is not the symbol. This is a cross section diagram. What is the symbol? The symbol for a transistor this is the symbol for a N-MOS transistor. Okay, so 3 terminals. Sometimes if you want, you can show the 4th terminal, but generally we don't show the 4th terminal in digital circuits. It will just be shown with the 3 terminal device. Okay, and this separation between the gate and the source and drain is to represent this oxide. The oxide doesn't allow the gate voltage to directly come in contact with the substrate region, which is here. Okay, so this is the circuit symbol for NMOS transistor. Circuit symbol for PMOS transistor. Okay, almost the same. Only difference between NMOS and PMOS is the bubble here, because NMOS and PMOS, as we will see, they are in some ways opposite of each other in the operation part. So because of that, the bubble generally in digital logic or digital electronics means inversion. Because both of the functionalities are inverted with respect to each other, there is a bubble for the circuit symbol of the CMOS transistors. So whenever we are drawing circuits, these are the 2 symbols that we will use. We will not see this full thing. Okay, this is just for us to understand the operation, which is what we are going to see next. Okay, so this 1 or 2 more things also we can write. I'll just remove some of these things to make it look a little bit. Okay, so source, gate, drain. Don't have to worry about the 4th terminal. Okay, so these 3 terminals are all that we need, and this region, so few things you can see here. Okay, this is basically slightly very small region, not so important, but generally the gate will be completely covering the in between part. This part, okay, is very important. This particular dimension, which is always represented as capital L, is the length of the transistor. This is a very important definition for many reasons, because this is also technology node. We discussed this in the previous unit. Any particular circuit that you are designing, okay, eventually it has to be fabricated. No one just does circuits for fun, right? If you look at any company, anything that a designer is doing, okay, he might be working at the layout level, he might be working at the circuit level, any level, eventually it has to be transformed into a silicon circuit, and whenever that happens, that will happen in some particular technology. Not necessarily that everybody always builds in the most advanced node. Okay, for example, there are automotive electronics. Automotive electronics doesn't need to be as fast as your microprocessor, because automotive electronics is connected to mechanical components, and as you know, mechanical components, they don't operate as fast as electronic components. So somebody who's designing something for an automotive company, okay, generally it will be companies like Intel, AMD, etc. But they will get specific projects for automotive electronics. So they might not always work in the most advanced technology, right? They might work in some older technology like 180 nanometer or 65 nanometer or something. But any circuit, okay, at the end of the day, it has to be fabricated in some particular technology, and that particular technology node, okay, is actually nothing but what is the length of the transistor in that particular technology node. What is the size of, even they might not even say length of the transistor, they'll just say what is the size of the transistor, because by size of the transistor they are meaning the length of the transistor. What is the size of the transistor in 90 nanometer technology node? I mean, it is 90 nanometer, right? It is, both are equivalent. That's why I'm saying both are the same. And in terms of the design rules, right, we also saw these layout design rules, that L, okay, is equal to 2 times lambda. Okay, whatever is the lambda for that particular technology node, this is equal to L by 2. So these are all equivalent definitions. That is why that particular term is very important, technology node. That is the first thing. Second thing is, for any circuit, okay, suppose I am designing some particular circuit. So for example, you might design something like a DSP circuit, or you might design something simpler like 8-bit, what can I say, 8-bit for some channel coding or for something simple, right? You might design something simple, but all the transistors in that particular circuit, right? Suppose I'm making a digital circuit for some functionality. All the transistors will have the same length L. There will not be one transistor which is 180 nanometer. Suppose I'm working in 180 nanometer technology. Okay, there will be no transistor at say 360 nanometer or 300 nanometer or 1000 nanometer. Nothing. Okay, all the transistors uniformly, they will have the same size, which is 180 nanometer, which is the length of the transistor. This is the definition. Now you might ask me, okay, you keep saying length, length. What is the width of this transistor? Okay, so for the width of the transistor, now I'll draw a diagram. It might not be so good because this has to be three-dimensional, okay, but I will try. The same diagram, okay, we will not do NMOS and PMOS because both are equivalent to each other. I will just draw the diagram for a PMOS transistor, and there I will try to show the width of the transistor. So same cross section only. Okay, so this is the same n plus n plus. This is, you imagine that I have cut it and I'm showing it to you, but actually it will have a third dimension also. So this is basically my three-dimensional diagram, and okay, so this will extend. That is, the gate will extend up to this point, and this is actually the full transistor. That is the three-dimensional view. Okay, this is L, still the same, and the N plus is extending along this direction on N plus extending along this direction, and completely through the length through this thing, it is having the gate on top. Now this third dimension is the width of the transistor. Okay, so width and length, generally when there is a length for any object, there will also be a width, and this is the width of the transistor, this is the length of the transistor, and together this whole thing is my transistor, MOS transistor. In particular, since this is N plus N plus, this is a NMOS transistor. Same thing for PMOS also. If you just change this to P plus, gate is still on top, no difference. Okay, this is the width, this is the length. So NMOS, PMOS, and this is the full diagram. And we are eventually going to talk about current flowing through a transistor, and for that particular definition, okay, for this course at least, I mean, current is everywhere. There is nowhere that current doesn't flow. Anytime you apply a voltage, current will flow. But there are many types of current. We are only looking at, okay, one current. And what is that current? That is between the source and the drain, or drain and source, but only between source and drain terminal. So I will just write that also, it's very important. So we are talking about MOS, okay, MOS current flow. Whenever this is from a practical perspective, when they say MOS current flow, they are talking about the current okay, only one current, source and drain. Between the source and the drain, what is the current flowing? And this current, we are also going to call this as IDS. Okay, NMOS or PMOS doesn't matter. From now onwards, all the things that we are talking about is for NMOS or PMOS. Okay, wherever there is a distinction, there we will write separate things. But in general, IDS is the current that we are talking about. The main reason why there is no other current is, in this structure, okay, there is a insulation between the gate. There are three terminals only, right? There is source, drain, and gate. Bulk is only for the support. It is not for current conduction. It has no electrical properties as such. Okay, it's only for support. And this three terminals, the current is only IDS. Why G is not there in any of the current expressions? Can you guess? It's very simple, right? Because the functionality, the way this whole transistor is designed, is that the gate terminal, okay, should not participate in current conduction. It should be isolated from the rest of the transistor. Okay, if it is completely isolated, then what is the point? There's no point in gate at all. So it is not completely isolated. Okay, I can put a voltage in the gate terminal, and there will be a electric field. There are two things: electric field and current. Electric field is just the force. Okay, if you remember way back, there is the equation F equal to QE. This F is force, E is the electric field. So the gate terminal, okay, is only responsible for producing that electric field, and because of the electric field, okay, the charges, this Q is the electron charge, but it could be electrons or holes, they will experience a force. Okay, depending on the voltage, either they will get pushed away or they will get pulled towards the force, because there can be only two types. right? And that is why we don't have any current. The insulation, okay, does not allow any current to flow from the gate terminal. So if you go for some higher level course in VLSI, or even during the lab, as you will see, there are leakage currents. So we said that this oxide is thin oxide, right? Thin oxide means, you can ask, how thin is it? What is the value? Value can be very small. Tox, okay? It can be very, very small. It can be 10 into 10 power minus 10 meters. Angstrom is generally used sometimes for this oxide, this thing, because we are at a very, very small level. Why nanometer is not used, why angstrom is used, that again is largely historic, because earlier on they were measuring in terms of the wavelength of light. So we will still continue with angstrom for oxide thickness, but this is the example of how thin this is, okay? Again, previously also we explained, if it is too thick, then it will be too high, the electric field, okay, it cannot penetrate the oxide and reach the substrate, so it will not be able to attract any electrons. So that is why if it is at very, very low value, then the chances of attracting the electrons are better, it's good, okay? And because it is very small, thin oxide, okay, there will also be some current in this direction. That is all part of the leakage current in this course, okay? In all the 5 units, we are never going to calculate any of that. It is there. If you, whenever we do the lab, you will see that there is also leakage current, which is given as the part of the overall power consumption, but we will not calculate that. So only remember, whenever any problem, they will, every time they will not say calculate the drain source current, calculate the drain source current. We are only talking about one current that is flowing between the drain and source. This is the first thing, okay? First point. Second point, okay, charge carriers. Whenever we have a current, there should be some particles that is responsible for that current. Current be of some magnitude, say half ampere, 1 ampere, how many ever amperes, right? But that current should consist of some particles, and that should represent the current. So in NMOS transistor, the charge carriers are electrons. PMOS, charge carriers are protons. No, okay? There are no protons in semiconductors. We are not talking about electrons and protons. In semiconductors, we have 2 types of charge carriers, electron and hole, okay? Holes, not P plus, P, sorry. Electrons and holes. These are the charge carriers in semiconductors. In particular, one distinction again between BJT and MOS transistors. In BJT, there will be both electrons and holes. Together is the current. That is, the BJT current is comprised of electron current and hole current. Generally, one will be much larger. That is true. But there will be some component. Generally, the quality of the BJT depends on how much bigger one is. But here, no confusion. Okay, there is only one type of charge carrier which is responsible for the current. In NMOS transistor, it is electron. In PMOS transistor, it is the hole. There are no 2 types of charge carriers are not there. Only it is one type. So MOS transistors are also called as majority carrier device. Okay, we don't care about the minority charges, we can just ignore them. They'll actually be very, very less. So majority carrier device, current between source and drain, electron current, hole current. These are the three things to remember about the current. Okay. Now next thing is, what is the mechanism? How does the current actually flow? So for that, we need to look at the structure of the transistor and what happens when we apply. Now the gate has to come into the picture. Gate voltage is responsible for the current, right? So we will redraw the two-dimensional cross section and look at different modes of operation based on the gate voltage. Now we have to look at the gate voltage because we are trying to on or off the transistor. Okay, so we'll redraw that diagram. Okay, so Mos transistor, modes of operation, and mode, we will see what are the modes, but mainly the thing that is changing here is the gate voltage. So because the gate is responsible for turning on or turning off the transistor, in the next few diagrams, right, we will cut off the source and drain terminals. Source and drain terminals, okay, they are responsible for the current flow, correct? Okay, no doubt about that. But the gate is the terminal that is responsible for on or off. So we will analyze the transistor in terms of the value of the gate voltage, and then eventually when we are looking at the current expression, definitely the source and drain will come back into the picture. For now, we will just look at the middle part of the transistor where we have the gate, okay, and then there is the thin oxide and there is the substrate. So we'll look at just that part. That is the first thing. Another thing is, it is little easier to analyze NMOS because we are familiar with metals, right? And in metals, the charge carriers are electrons. In NMOS transistors also, charge carriers are electrons. So for all practical purposes, they are equivalent to metals. So everything that we do, we will do for NMOS transistor only. Towards the end of the derivation, that is when we are finishing with the current derivation, then we will see how to apply it for Cmos transistor also. Almost 95% will be the same, except some very important conditions. So first we will look at NMOS transistor only. Okay. Okay, I've drawn the full transistor, but we are focusing on the middle part because the gate, okay, directly the gate cannot affect the source and drain terminal because source and drain terminal are also electrical terminals. There will be some voltages which is given separately to those terminals. So those values we know because we are only applying that voltage. So don't worry about the source and drain terminals for now. Only we will look at the gate voltage. Let us call it Vg for now. Okay, that is the value of the gate voltage, and we have our source and drain terminals, but we are looking in the middle part. So first, assume Vg lesser than 0V. Actually, this is not possible in practice, okay? And the reason it is not possible in practice in digital circuits is we have only two voltages. We have only uh, we have only ground, which is 0, and VDS or VDD, which is power supply. So just for our understanding, we will see what happens somehow if I get a negative voltage from somewhere, okay, and I apply that to the gate terminal. What is the value of the gate voltage? So that is what I want to see. And we can understand this from common sense. Okay, we have a p-type substrate here. We have two regions here called the source and the drain, and in these regions, okay, one type of carrier dominates, and in this particular region, the dominating one is the electron because it is n plus. So this might be something like, say, okay, the numbers are not very important for us, just an example. And n plus means there are 10 power 17 per centimeter cube of electrons available in that region. That's a lot, okay, 10 power 17 is quite high. And holes in the substrate, that is where it is just p, not p plus, okay, where it is just p, it might be around 10 power 15 per centimeter cube. Now, even though this is 10 power 15, okay, in this region, therefore, n, this is the thing that we have to understand. Even though it is a p-type substrate, okay, the electron concentration is not zero. Nowhere anything is zero in nature, okay, absolute zero is not there anywhere in nature. And here also, even though it is a p-type substrate, doesn't mean that electron concentration is zero. There is an equation, okay, which tells us that ten power 20 approximately, okay, not exact. There is an equation, if you remember solid state electronics, you will not remember because that subject was removed. But if you look at the physics behind all these, in that one very important equation is there, which tells us that in any semiconductor, okay, sorry, not in any in silicon, under room temperature, okay, the product is a constant. And what is the value of that constant? It is approximately 10 power 22. That is the concentration of electrons and concentration of holes. If you multiply them together, okay, we have some numbers here, right? You will always have the same value, which is 10 power 22. So if I go backwards from this relation in this region, already this is 10 power 15. So this is approximately 10 power 7 because the product has to become together 10 power 22. So in this picture, okay, I have NMOS Vg lesser than 0 volts. So in the substrate region, okay, it is not 0 electrons. That is what I was trying to tell. There will be some electrons, some 10 power 7 equally distributed along the substrate, okay. And if I apply a negative voltage, those electrons in this region will all get pushed deep inside because this negative voltage, I am applying a negative voltage now, negative and negative, electrons are negatively charged, they repel each other, okay, and they will all get pushed. Plus, what else will happen is, these majority charges, that is the holes, they will all get attracted and directly sit below the gate terminal. They cannot go into the gate terminal because of the insulation. Okay, you imagine there is a sellotape. The sellotape will insulate the, it will not allow whatever water or something to pass. So there is an insulation. So all the majority holes, which is from the p-type substrate, okay, they will redistribute themselves and they will all come and sit directly under the gate terminal because they are seeing this very nice negative voltage which the holes like. So this is what will happen when I apply a negative voltage. This type of mode is called as the okay. So accumulation mode, it is called accumulation mode because the majority charges. What is the majority charge? This is a p-type substrate, and directly from the numbers also you can see which charges are in majority, which charges are in minority. It's like super majority and super minority because there are some 10 power 8 times more. Okay, that is it is more by 10 power 8 times. So this majority charges are the holes, and in this mode of operation it is called accumulation mode because the majority charges accumulate in the channel. Now this is a very important term that we are defining now. Channel region. What is the channel region? Channel region region directly below what? The gate terminal. That is the region of the MOS transistor directly below the gate terminal is called as the channel region. Okay, this is very important because we said that we want the the MOS transistor to operate as a switch, and it should operate between the source and the drain terminals controlled by the gate. Now the channel region is very important for this functionality because somehow if I can connect these two, okay, it has to happen through the channel region. It cannot happen through the substrate because substrate has no properties. It is only for support. It cannot happen through the gate because there is an insulator. So the only way in which the source and drain is connected, if somehow I can connect it in the channel region. That is, channel region is very important for our functionality. That's why it has a special name. Okay, it is where all the functionality of the MOS transistor is focused upon. It is focused upon the channel region. Now let us look at this configuration, which is also called as accumulation mode. Okay, so I have two n plus regions which have to be connected together if the switch is on, which have to be disconnected if the switch is off. So in this mode of operation, okay, can you tell me if the NMOS transistor is on or if it is off? That is the question. Okay, so NMOS transistor, is it on or is it off? There is no chance of it being on, right? Because